So there's going to be some multiple recordings here. Okay. So I'm going right to the example. Notice I'm not going right to a theorem. I'm going right to an example because the example is going to help you understand the theorem. It's just my style, but I'll let you copy this example down. Mention too while you're copying. So I know that many of you are taking, copy down notes, and I think it's a good idea to write notes down because it helps you, as many of you mentioned in the first day class, it just helps you retain the material better. It helps you remember the examples, and it even helps you understand. So I try to pace myself through the examples so that everybody should have time to copy the examples down. I know some folks copy things a little more quickly than others, but I try to pace myself so everybody has a chance. And I ask frequently if everybody has the example copied, because that's what I would do in class. All right, so let you copy the example. Oh, thank you, Solomon. I appreciate that. Okay, give you just a little more time. Okay. So in this problem, we want to solve a homogeneous system. Why is this? Well, first of all, what are these two? We have two equations in our system with three variables. Geometrically, what would those two systems be geometrically? Where do they live? Do they live in R1, R2, R3, R4? Where do those they live in? That's right, Max. They live in R3. Solomon, Mikkel, yes. These are two planes that live in three-dimensional space. Now, that's right, Devahar. And you know, we don't have an X, Y, and a Z anymore. We have an X, I mean, we could, but we need to get used that we're going to be dealing with many, many, many variables. So X1, X2, X3, three-dimensional space. Why is this called homogeneous? Can anybody tell me? I mean, and then, you know, below it says solve the non-homogeneous system. So Noah's right. The first system corresponds to A times vector X equals 0. When you have a 0, when you have zeros on the right side of the equal sign, it's called a homogeneous system. The second system, the A is the same, right? The A is going to be that 2 by 3 matrix with on the first row 1, 4, -5, and on the second row 2, -1, 8. The second system of equations is AX equals B. And B is not equal to 0. B is equal to 0, 9. So the idea, I mean, there's several things going on here. Is there a connection between the solution to the homogeneous system and the solution to the non-homogeneous system? Okay, we want to know if there might be a connection. All right, and to that end, we're going to work this problem through. And then we'll describe the solution sets for each of these systems. Are there any questions before I move on? Does everybody have the example copied okay? Let me know if you didn't, you know, let me know if, okay, thank you, Sab. Vivian, thank you. Okay, all right, then I will move here to the solution. So we're going to worry about the first system here. What should we do? Kevin says, what's the symbol above the X called again? That's a vector symbol. Yeah, this is a vector. And when you write vectors in the textbook, thank you everyone, the vectors are bold. When you see a bold symbol in the textbook, it's a vector. But when you write it out, like on paper or for your first exam, when I'll go into some detail about that, if not Thursday, definitely next Tuesday, because your first exam is going to be next Thursday. But I'm still working through the details of, you know, how it's going to be constructed and so forth. But, you know, writing the work, showing the work, this is how you show the vector X. Good question, Kevin. Any other good questions? Okay, well, let's get to our solution here. So, of course, that's right, Matthew. This is what we're going to do. We're absolutely going to do that. We're going to set up our system of equations as this augmented matrix. And we're going to try to get the augmented matrix in reduced echelon form. Okay. Okay, so of course, the one, what's that one up in the top left corner called? Good, good, it's a pivot. We use pivots to produce zeros in the column that the pivot's in. So I want to get a 0 where the 2 is. So I'm going to take the first row, multiply it by -2, and add it to the second row. So I'm taking really the first equation, multiplying it by -2 in my mind, and then adding it to the second equation in my mind, and I replace the second equation, the row 2, with that result. And this will be what we get here. Okay, a question's asked here. So what I'm doing is I'm putting in the I'm describing the row operations here, so it's in your notes. On exams, should we write out the row operations? I might ask you to do that. That's again, Matthew, something I want to think about, but I might ask you to do that. Let me see. Do I have an error here? Let me see. Well, hold on. -2 times -5 is 10, and 10 and 8 make 18. There's a question on the 18 here. No problem. I want this. This course, we're trying to get as close to an in-class on campus, course as we can, and so questions are good. All right. Now, what do we want to do next? Let me see. On your notes, you're writing the row. Yeah. So what happens is when I get to the next augmented matrix, I write the row operations that I did to the right of that, so you can see what I did. You could put on the left. The tilde is usually put here to show that the first augmented matrix is equivalent to the second augmented matrix. I'm flexible. I think it's better to have the row operations to the right, but I'm flexible on that. Now, what do we want? Oh, okay. That's okay, Matthew. That's okay. Okay. And what do we want here where the -9 is? If we want to get the matrix in reduced echelon form, what do we want there? Place that -9. That's right, excellent. We want a 1. So of course, what we have to do is we have to take the second equation, multiply it by -1/2, and then put that result in for the second equation. And that's what was done here. So now we're down to here. Are there any questions so far? All right. What form is this matrix in? What form is this matrix in? Is it in reduced echelon form? Not quite. Not quite. Why isn't it in reduced? It's in echelon form. It's in echelon form. To get it in reduced echelon form, what do we have to do? What has to happen for it to be in reduced echelon form? I'll give you a little hint. Look at the second column. You have a pivot of 1. That's right, Matthew. The 4 here needs to be a 0. That's right, Ryan. You need a 0 above that 1 pivot. Okay. So we're all right. So we'll take the second equation, multiply it by -4, add it to the first equation, and replace the first equation with this result. And that gets us in reduced echelon form. Okay. Okay, so now we've done all the row operations that we can basically, well, we've simplified the matrix really, or the augmented matrix as good as we can do. And now it's time to think about solutions. So here you have two different equations with 3 unknown variables, right? So what are we going to have in the solution? What are one of the variables going to have to be? A free variable. That's right, Solomon. And you can let any of the 3 variables, x1, x2, or x3, be free. But I find it easiest to work backwards. I let x3 be free. The second row, of course, the second row reads 1x2 minus 2x3 equals 0. Right? So that means then that x2 is 2x3. On the other hand, the first equation reads 1x1 plus 3x3 equals 0. Right? I mean, we remember now, we didn't when we did the augmented matrix here, we didn't, well, I want to say, so just because, you know, we do it so often, we don't put, like, I've seen this in other books where for an augmented matrix they put like dashes between, you know, they put dashes there to separate the constants from the coefficients of the matrix A. But, you know, we know what we're doing here. So this means then that x1 equals -3x3. Okay. All right, so far, are there any questions? Everybody has it, the example that so far. I want to move to the next slide. So let me know if you, yeah, Divahar, question? Okay, Divahar has a question. Let me see. Oh man, Divahar pointed out something. I have a little error here. Thank you. Let me point that out. So here, on this step here, it should be a -1/9 instead of a -1/2. Thank you. Well done. Well done. So I'm taking the second row. Let me just clear that. I'm taking the second row over here, and I'm dividing by -1/9. Okay. And that'll be reflected in the recording as well. Good catch. Good catch. Thank you. Okay, are there any other good questions? Okay. So what we want to do now, let's go ahead and move to the next page. The solution then, if we just write the solution as a vector, this is our solution. The vector x equals the solution vector x, okay, equals the vector x1, x2, x3. And I just put in what x1 and x2 and x3 are. We knew x1 was -3x3. We knew x2 was 2x3. And x3 is just x3. But in this problem, we want to describe the solution set for the system. So this is nice. We have a solution, but what does this mean in regards to the two planes? What does this mean? Well, to help us, what we can do is we can write the solution x in what's called parametric vector form. So notice between the three in the vector x, the three entries, they're all functions of the free variable. So I can factor out the free variable. Okay, I can write my solution vector x as x3 times the vector v, which is -3 times 2 times 1. x3, which is the free variable, is called the parameter. Okay, that's called your x3 is your parameter. I don't want to clutter it too much. That's your parameter. Parameter. It's like, remember when you had in calculus like the t? Parametric parameters, parametric mode. but now, yeah, but now the parameter is the x3. It's the free variable. Thank you. So that's why we call it parametric vector form. Every one of the entries in the vector is the function of this parameter x sub 3. Now you might be wondering why, why does this matter? Well, remember originally we wanted to describe the solution set for the system. It's helpful to write the system in this parametric vector form. Okay, because now we can say, and I wrote it out in a nice sentence, the intersection of the two planes. Well, the two planes intersect, right? So how two planes would either they're going to intersect, either they're going to be, if they're the same planes, they intersect everywhere. But if the two planes are not the same, but yet they intersect, then the two planes would have to intersect in what? The two planes have to intersect in a line. That's right. So it's not, that's right, Matthew. So sure, these two planes intersect in a line, but we'd like to describe the line. We'd like to describe the line. I mean, it's not just any old line, right? It must have some properties. Okay, so what you're doing here, if I draw a line, let me see what I can draw here. I can't really draw a, well, hold on. What I'm doing is I'm drawing a vector. So this vector v here, I'm going to call this vector v. And I'm drawing the vector from the origin. Okay. So what I'm doing is I'm geometrically looking at my parametric form of the vector, a parametric vector form of the solution, and trying to figure out what kind of, describe this line. So let me ask you this here. Would the points on this red line be part of my solution? What I've done is I've drawn a red line. I haven't drawn a full line, but I've drawn like half of a line. From the origin, this line goes through the vector v in the direction of v. Okay, all right, and many of you are saying yes. Well, let me ask you this. Let me ask you this here. So if let me just kind of put a coordinate here. That coordinate is, since vector v, it's vector v, and vector v is -3, 2, 1. And this is, you know, I'm drawing it in 2 dimensions, but we know it's like, we know where it's a 3-dimensional vector. I'm just drawing a little, it's just kind of a geometric, to give you a geometric feel. That's -3, 2, 1. Now, what would x3 be at that point? What would the value of our parameter be at -3, 2, 1? That's right, Wastina. x3 would equal 1. x3 would equal 1 because 1 times -3, 2, 1 is -3, 2, 1. Let me put another point here. Can you give me an idea of what that point is gonna, what the coordinates are gonna be? This second point here. Well, you're almost right, Wastina. Well, Siab, the origin is 0, 0, 0. Okay, that's right. Wastina, Mikhail, and Robin. It's going to be -6, -6, 4, and 2. Because this point here is basically, if I took the vector v and doubled it, right? If I took the vector v and doubled it, wouldn't that get me to -6, 4, 2? By the way, what would x3 equal at -6, 4, 2? x3 would be 2. That's right, Rob. So you see, by taking different values, by setting my free variable, my parameter, by letting it take on different values, I'm constructing different points. I'm finding different points all on this line passing through vector v1. So, I mean, we can let x3 take on different values, and we're going to produce other points also. And I could let x3 be like, you know, 5 halves, or, you know, 12 sevenths, or, well, I guess it would have to be a little more, like 15 sevenths. You know, anything you want, but you're going to create a bunch of points, okay? And all these points are going to continue extending that line. So does that make sense so far? Are we good so far? Are there any questions? Can the parameter take on negative values? Absolutely. Okay, so to get that then, negative values, when the parameter takes on negative values, I'm going to be, man, give me a line here, please. I'm going to be getting the other side of this line, so to speak. So, like, for instance, this point here, a little tricky here, but I like this point here, make it kind of a big fat point. That would be what? That would be, what would that be? 3. Okay, Solomon's right, and Wastina I think that, I don't know, I think that means agree. There. Okay, thank you, Westina. I didn't grow up with cell phones, so I'm not aware of all these chat, well, I'm aware of some chat things, but that's right. 3, -2, and -1. Because this here, if V1 is here, then this is going to be -V1. And I could even, I'm sorry, V. I could have, like, instead of V, just 1V, right, over there. And this is -1V. And so for -1V, what's the value of the parameter? This -1V. What's x3 going to equal? That's right, Solomon. x3 equals -1. So it's very clear then that the intersection of the two planes is a line, right? It's this line here. We could, you know, we know a line has, we denote a line with the little arrows there. It's a line parallel to the vector -3, 2, 1 and passing through the origin. So by writing the solution vector x in parametric vector form, it allows us to be descriptive in terms of what the solution geometrically looks like. Okay, I'll give you a moment to copy that. So what Moshe is asking is, you know, what's the point of what I'm doing with this? What I'm trying to demonstrate is the solution, the set of points, forms a line in space. The line in space is parallel to vector v, which is -3, 2, 1 vector, and passing through the origin. So the way you generate that line is by taking different values of your free variable, of your parameter, letting x3 take different values. And I chose some easy ones. I let x3 equals 1, x3 equals 2, x3 equals -1. When I do that, I'm getting multiples of my vector v. And these points that come about by taking different values of the parameter and multiplying it by the vector all fall on a straight line. So what I've basically done is I've found 3 points that are part of the solution set by changing, by having the parameter take on 3 different values. Okay, that's what I'm doing. And so my hope is you'll see that if you let x3, the parameter, take on an infinite number of values, you're going to generate this line in space. Parallel to the vector v, passing through the origin. O'Shea, does that make sense? Okay, you're welcome. All right, are there any other good questions before we move on? All right, well now we have another part. We have to solve, so we know what the solution to the homogeneous system looks like. Now we want to get the solution to the non-homogeneous system. So let's go ahead then and work that out. So the non-homogeneous system, the row operations are the same as what you did with the homogeneous system. So I didn't bother rewriting them down, but I mean, I guess I can if you want here. Now notice we have a 0 and 9, 0 and 9. Those are our constants in the augmented matrix. If you hear a clap sometime, by the way, it's because I got a mosquito flying around here. And, you know. Okay. Okay, so I'm taking this is sort of try to write it a little nicer. These are just the same row operations that we used before. That's -4. I want to make it a little bit nicer. I mean, this should be an easy one for you all now. You've dealt with some pretty big matrices, right? Okay. So this is going to be then the solution for the non-homogeneous differential equation. Are there any questions? Okay. So what should we do next? Now that we've found the solution, what should we do? What should we do next? That's right, Mikhail. Put it in parametric vector form, and that's what we're going to do. So I'd like to move to the next slide, but I want to make sure everybody has this copied. Is everybody good? Does anybody need more time? Just let me know. All right. All right. So then, here we go. Here's the solution vector. But now I have to write it as the sum of two vectors. Well, I can write it as the sum of two vectors. You have a 3×1 vector here and a 3×1 vector here. And when vectors are of the same size, you can add the vectors entry by entry. So writing the single vector with entries 4 minus 3x3, -1 plus 2x3, and x3, I can write that as the sum of the two vectors over here to the right. The sum of the vectors 4, -1, 0, and other vector -3x, -3x3, 2x3, and x3. And you might wonder, why do we want to do that? Because it's going to help us write it in parametric vector form. Below is the parametric vector form for this solution. Okay. All right, class. I see what you're saying. I didn't have my sound on. I can't believe it. All right. Let me go back here. Thank you. I now see where you were confused. So okay, we have here. Thank you. We have here the parametric vector form, and what I want to do is I want to show you geometrically what that parametric vector form means. So do you see that there is it resembles a little bit? Well, all right. Let's just write out what this is going to be. So geometrically, we want to understand what this parametric vector form of the solution is showing us. So what I've done is I've drawn just a vector P. I've drawn a vector P here. Okay. Here it is, vector P. Okay. From the origin. And then I've drawn a vector V, tip to tail from P. And what I want to ask you is this. What is that purple vector equal to? That I just drew there. That's right. Good, Salman. Good, Westina. It equals P. Gotta switch it here. This equals P plus V. Now, if that vector equals P plus V, what's X3 equal to? What's X3? What's my parameter equal to? 1. That's right. X3 equals 1. Okay. For this point right here, so I'm putting points down to see what this line looks like, putting some points down. But to put the points down, I have to set values of my parameter. Okay, what's this point here going to be? What's the X3 going to be for that point? This point right here. Zero. That's right. Good efforts. Good efforts. Because here, this point here, and I'm putting it in parentheses, X3 would equal 0. Okay. Okay. And what's going to happen is, of course, what about over here? That point there. what's this vector going to be? Yeah, that's P minus V. Right? This is P minus V. P minus V. And so there, that point, I'll put it in black, x3 equals -1. x3 equals -1. So you can see what's going on here. You can see it. This is the line that's being traced out. Forget about that black, it happens. Forget about, this is just junk here, this line. But this means that the intersection of the two planes is going to be a line passing through 4, -1, 0, parallel to or in the direction of vector V. And I don't want to erase that. This happens occasionally. There'll be like some big line that goes through the paper. Just ignore this big ugly line. It's nothing. Okay. This is what the geometrically what the solution is going to be. Again, by letting the parameter take on different values, you're able to you know, get a feel for that, for what the solution is geometrically. Basically, it's the solution of the homogeneous equation shifted by the vector P. It's the solution of the homogeneous equation. I'm going to say this right. The solution of the non-homogeneous equation geometrically is the solution of the homogeneous equation, but shifted by that vector P, which is a particular vector P. How many differential equations have heard of like non-homogeneous solution being the sum of a homogeneous solution plus a particular solution? How many have heard of that? Maybe if you've taken differential equations, I don't know if any of you have, but okay, you all know what I'm talking about. Well, it comes up here too. It comes up here too. Okay, so are there any questions on this? How many find the geometry, the little pictures, were they helpful in you feel comfortable? Oh, good, thank you. Thank you, Rustina, Solomon, Kevin, Matthew, learning all your names. You, wonderful. And I'm hearing from people I normally know, Christy, Vivian, Francesca, wonderful. So yes, Divahar, indeed it does complement it, yes. So I'll move to the next page then, if I can, if we're good. All right. So what you're doing, you're really reinforcing this concept, this theorem 6. It says, suppose the equation ax equals b, okay, and that by the way is the non-homogeneous equation. Suppose it's consistent for some b, which ours was, and let p be a solution. Then the solution set of the non-homogeneous system of equations is the set of all vectors of the form p plus vh, where v sub h is any solution of the homogeneous equation. So, and I'll go back to that, but basically what you had here, the homogeneous system, right, that corresponded to ax equaled 0. That's what that corresponded to. And hold on, now wait. Let me just make sure we're good here. I was on the wrong side, sorry. This here was ax, thank you, equals 0. That was what this system represented as a matrix equation, the homogeneous system. And then the non-homogeneous system was ax equals b. Where b was 0, 9. That's your non-homogeneous system. There's the matrix equation for that. And you can see that the connection between the solutions to the homogeneous and non-homogeneous differential equation follows this theorem. The solution set to the non-homogeneous equation, ax equals b, is the same. It is the set of all vectors where you have a particular solution vector p plus the solution to the homogeneous system of equations. Okay, are there any questions on that? Okay. Now, incidentally, they have also another example that I think is pretty cool. This second example, hold on here. It's in your book, but it's example 2. So it says, describe all sets of the homogeneous system. This is example 2 from the book. And the homogeneous system is 10x1 minus 3x2 minus 2x3 equals 0. Well, that's a plane, right? That's a plane. And the plane passes through the origin. But, you know, can we get more than that? Can we understand more than that? And we can. Okay, just never mind the phone. Because we can write, well, what they're saying here. Yeah, hold on. I'm watching this. Yep. Okay, so what they're doing is they're saying the general solution for this example 2. Sorry about that. The general solution for example 2 is they solve for x1. So they say, okay, if we divide, or I should say really multiply through, because it's row operation, but if you multiply through all these terms by a tenth, then x1 can be, and then bring the x2 term and the x3 term to the other side, then x1 will be 0.3x2 plus 0.2x3. That's what they're saying there. And so in this problem, you have two free variables. And so you can write the solution then as the solution vector x like this. x1 is 0.3x2 plus 0.2x3. And then you can write that in parametric vector form. Okay, so the solution set is in the span of vectors u and v. And they're drawing a picture here of what the plane looks like. The plane is all linear combinations of vectors u and v. So if you draw u and you draw v, and just were to draw the linear combinations of that, you would generate a plane that passes through u and v. I want to say that right. It's a plane through the origin, but it also contains any linear combination of u and v. I think it's a really cool problem. How many think that's pretty cool? Yeah, I mean, this is the power of linear algebra. Thank you. Okay, thank you, Kevin, Mikhail, Robin, and Christy. Are there any questions on that? Francesca, thank you. Okay. All right, I want to do one more here, one more example with you. Let me just stop sharing this. That's in your book. Let me just. I was debating whether to do this or not tonight, but the thing is, I think this will be helpful for your multiple choice questions, this problem. So we'll just go ahead and do it. Something a little more theoretical. Okay, let me give you a little time to copy that down. Okay, so this is a problem where we have we're saying this is somewhat theoretical. We have a 3 by 3 matrix, and y is a vector in R3 as it needs to be. And we're saying that the solution, that the equation ax equals y does not have a solution. Does there exist, if that's true, does there exist a vector z in R cubed such that the equation ax equals z would have a solution? Okay. So this reminds me of a multiple choice problem. Okay. And maybe a difficult one. So what I think is helpful is trying to construct examples to help get an intuitive feel for the problem itself. So what I'm going to do is I'm going to make a little example here to help me. All right. So are we good with this example? Does anybody need more time to copy it down? Okay. Okay. All right. So the answer is going to be no. The answer to the question is no. Now let's see if we can justify this. And maybe what you would do, what I'm showing you now, is maybe you wouldn't say no yet, but since ax equals y has no solution, A cannot have a pivot in every row. Why? Okay, well, what I have here is what I call a supportive example. I'll give you a chance to catch up here. Okay, so what I've done is I've just written down an example of a system A times X, a system of equations, A times X equals Y, that does not have a solution. We know this system doesn't have a solution because the last row, the last equation, there's no x1, x2, or x3 that's going to satisfy that. But then if we, this idea of cannot have a pivot in every row, A can't have a pivot in every row, let's sort of see that. Well, if I take the system of equations and write it as the augmented matrix that I'm circling here, okay, and that would be equal in symbolic notation as the matrix with well, this is how we denote that augmented matrix. Right here. Clearly, I mean, I've identified then what A is and what Y is and what X is. which isn't hard, but what's important is the matrix A. The matrix A has no pivots in the last row of A. So this is something that is important in order to answer this question. If this system of equations, ax equals y, does not have a solution, then that means that we have to have one of the equations such that is like this last equation here, right? And I'm doing it with three equations and three unknowns. You could do it with two equations and two unknowns. But the point is that, well, that is correct, Evahar, what you're saying about ax equals z, that it'll have infinite solutions or no solutions. But clearly there has to be then, since the system has no solution, there has to be a row of pivots in A. So how many of you does it help to sort of get a feel for the problem? I mean, it's a little abstract, but does it help it be more concrete by writing down a little example to convince yourself? How many feel that's helpful? Okay, good. Excellent. And thank you. So now what I'm going to do is I'm going to work with this ax equals z. Okay. Thank you, Michael. Thank you, everyone. Now I'm going to work with ax equals z. So may I move to the next page? Are we good so far? Okay. Yeah, I just made up these values. I made them up. This example here is my made up example. It's not from the book. It's my example. My example. Okay, good. My example. Okay, so now let's work. If ax equals z has a solution, the solution x must have at least one free variable. It has to. Why is that? Because what I'm doing is I'm writing a system down where I keep the matrix A that I had, and then I have this vector z here. But being, let me make that a little, but being that the matrix A had 3 zeros for its last row, the only way the system of equations is going to have a solution is if the vector z, that vector of constants, has a 0 also as its last entry. It has to have a 0 also as its last entry. But then if it does, that means you're going to have a free variable. You have to have a free variable in the solution, and so therefore the solution x is not unique. The other option would be you could have it where the system doesn't have a solution, but I'm just going to, hit on the touch on this right now, because there's definitely no unique solution. The solution will be either be an infinite number of values because you have a free variable, or there will be no solution. And that would be if the third entry in your vector z were a non-zero value. I find it so helpful for these multiple choice problems to just write down some kind of cookie cutter examples, as you might say, to help me think through what the solution could be, what the solution is. Okay, are there any questions on that? Thank you, Divahar. Makes sense to Divahar. Good. And you know, sometimes it takes a little time. It does. You know, it takes me time to feel comfortable. That's why I do these examples. I mean, I'm not gonna, you know, I'm gonna do anything I need to do in terms of thinking of examples to help me get these multiple choice questions right. I don't want to just guess. Okay, on the exam, for instance, you might have to show some supporting examples for multiple choice question. All right, let me stop the recording there.